Today we'll talk about the faithfully flat descent. This is a very important tool for computation of Dahl homology and has many other applications. Flat descent. Okay, so this is a general name for many different for a class of results. So here is one question, a typical question this theory addresses. So suppose we have some scheme X and a morphism from Y to X. And suppose we are also given a morphism from Y to some scheme Z. So we want to, let's give some name. So let's call this pi, and this is phi. So the question is whether there exists, whether this morphism phi descends to a morphism from X to Z, making this diagram commutative. So let's call it psi. So what we want is a unique psi such that the composition of pi and psi is equal to phi. So, well, what does it mean? That's, well, in general, of course, this psi need not exist and it need not be unique. For example, if we just take for x, y plus a single point, then we can define psi arbitrary at this single point we add. So to make this question more reasonable, let's to have a chance for the uniqueness, let's assume that this morphism is surjective. Well, in this case, at least it's reasonable to expect that, set theoretically, for surjective map of sets, given pi and phi, there exists at most one psi making this diagram commutative. Clearly, right? So if this is surjection, you just take how you define phi. You take an element here, you take its preimage, and then you apply phi, and that's declare this to be the psi of your point in X. Well, but clearly this psi, though for surjective map of sets, psi is unique if it exists, it need not exist in general, because this map phi need not be constant on the fibers of this map. So we want to impose an extra condition saying that phi is constant on the fibers of this map. So here is a nice way of phrasing this. So let's consider the fiber product of y with itself over x. Then we have two projections. And so composing this projection with phi, we get two different maps. So this is, sorry, this is P1 and this is P2. And let's assume that the composition P1 composed with phi is equal to phi composed with P2, right? So these two arrows are the same. So if x, y, and z were just sets, then these two conditions, this condition and the surjectivity of pi, would guarantee that such psi exists and unique, right? Oh, sorry, something is wrong here. Okay. Так, спасибо. Is it? I think so. Right. So I'm not sure whether it was visible what if it was possible to hear what I explained at the beginning. So we are discussing faithfully flat descent, and so the question is, given a morphism from surjective morphism from y to x and a morphism phi from y to z, who is the property that this phi is constant on the fibers of this map, meaning that we have this condition, whether there exists and unique phi with this property, whether this phi descends to x. So, well, and as we already observed, the answer would be yes if x, y, and z were just sets. But clearly, it's not in general. This psi need not exist even if we work with topological spaces or schemes. So, example, let's take just A1, and let's take for y, this will be our x, and let's take for y A1 minus 0, which is called GM, the multiplicative group, plus 1 point. This joint union spec K, right? So, and we have this map given by the inclusion and embedding spec K into the origin, right? This is a surjective map. So, and for Z, I want to take the identity map. Right? So, okay. So what is y times y over x? Let's compute it. Yes. And what do you get? Так, плохо слышно. Сейчас. Окей. Сам y получим. Ну, конечно. If you take the fiber product of GM and spec K over A1, you get empty scheme. If you take the fiber product of GM with itself over A1, you get GM, and here the same. So you get just Y. And this is the diagonal. So the two projections here are just equal. So this condition is empty. So you get two maps which are topologically, well, which are equal, but clearly this does not exist. This kind of map exists that theoretically, but it's not continuous. Does not exist. So we need an extra condition. So this map pi cannot be an arbitrary surjection. We want it to be a nice surjection. Okay, so that's like one atypical question faithfully flat descent addresses. So let me formulate an answer. So when the answer is positive. So, and in order to do this, I will introduce another type of topology. Oh, by the way, so let's before even here, so I want to introduce some terminology. So site is a category with Grothendieck topology. So we have a Tal site whose objects are Tal schemes over X and topology, well, given by surjective maps. And well, we have the risky site, and now we're going to have another site. Which is called faithfully flat, okay, so faithfully flat topology. Flat topology. Well, I will start with, so here is a definition. So suppose I have any scheme. So a family say of schemes over X is a family of flat morphisms is a faithfully flat quasi-compact cover covering. Okay, so this abbreviation stands for so Fidelmon flat and quasi-compact. Covering if the following condition holds. Okay, so for any affine open T in X, there exists a finite collection of affine open subsets of these guys, T1 affine open, T1 U I1 Tn U In such that the images union of phi I j, j goes from 1 to n, of all these guys, Tj, is my T. Okay? So this in particular, it implies that the map from the union of all this ui to x is faithfully flat. Faithfully means that it's surjective. By definition, a faithfully flat morphism is a flat surjective morphism. So this condition is a bit stronger than that. And so there is this word quasi-compact. And let me give you an example of a faithfully flat cover which is not of this type. So let's take just a fine line. And let's take for let's consider the following morphism from union, disjoint union of over all points, including generic point of A1, of spectrum of local rings at these points. So this maps naturally to A1. Yes, what is the question? Okay, this is my U. And then it's faithfully flat. But not faithfully flat quasi-compact cover. So I want to prohibit this kind of things. However, so what I can do, to give a sort of another example, you can take, say, GM, disjoint union of SPAC or A1, local ring at 0. 0 is closed point of A1, and this maps to A1, and that's okay. FPQS cover. Okay? So, now we have we can introduce faithfully flat site. So here is FPQS site. So our category C will be just the category of all schemes over X. And so this is a category, and now I have to tell you what are the covering sieves, and covering sieves by definition are those sieves that generated by faithfully flat quasi-compact covering. by flat quasi-compact covariance as before. Ui goes to x. Or maybe more general. I need not, this is a sieve over x, but I need to tell you, so y is in scheme over x. Okay. So here is a, this condition is a bit complicated. And so here is a lemma. So once we have a site, a category with growth-induced topology, we can talk about sheaves. Sheaves of sets or sheaves of abelian groups. And so I will tell you what, so a sheaf is in particular a presheaf, so it's a functor from the category of schemes over X to sets that satisfies certain sheaf condition. And I will tell you explicitly what this sheaf condition is. So a presheaf so let's call it F on schemes with this topology F, P, Q, C is a sheaf if it has the following, if only if, one is that F for every y for every scheme over X, F is a risky sheaf. Risky sheaf on Y. Okay, so a presheaf, well, I can restrict it to, so Y is a scheme over X, so I can restrict my presheaf to open subsets of Y and get a presheaf in the risk, well, presheaf on Y for usual open subsets. And I require this to be a sheaf, the risky topology. And the second condition is the following. For every morphism, for every morphism of affine schemes, spec B to spec A over X, right? These are schemes. The following condition holds. So if I, let me write it here. Нет, нет, любая. Ну, важно, что замена базы плоская. Значит, вот у меня есть какое-то решето. Значит, мне нужно проверить. So the question is why this is a growth-induced topology. So suppose I have, so what is one of the conditions is the following. Suppose I have a covering sieve, so it's generated by some UI. which by family of flat morphisms. And suppose I have any map from y to x, then I need to tell you. So what is a very good question, by the way. So we have. Let's discuss it in. So suppose this is generated by FPQC covering UI X. So, and okay, so now I consider, so what is one of the axioms of growth-induced topology is the following. If I consider the sieve that consists of all y such that, over y, such that this composition, such that y to so such that this is phi, this is psi, such that psi phi composed with psi is in U is a covering sieve. Right? So why that? I claim that this sieve, that's what we need to check, right? So I claim that this sieve is the sieve generated by fiber products. Ui times y over x to y. So these morphisms are flat. And, well, one verifies easily that it's actually a, well, it's clearly, it's the map from the disjoint union of these guys to y is surjective, so it's faithfully flat. With a little more efforts, one check this quasi-compactness condition that we had. So, so this is, I claim that this is FPQC cover. And therefore, the axiom of growth-induced topology is satisfied. Okay? Good. Yeah, so I want to, I haven't yet finished the... Что? Да, мы не требуем. Например, вот есть, this is also a very good question. So there is a version of a Tal site, which is called the big étal side, where you consider, for the category, you consider all schemes over X, not necessarily étal schemes. And covering sieves are those sieves that are generated by surjective étal morphisms. So in this case, well, the same argument shows that it's also a topology. So these examples appear in nature. Okay, so I haven't finished the second condition. So the first condition, so for F to be FPQC sheaf is that it's a Zariski sheaf, and the second condition is also understandable. It's the following. So if I take F and evaluate it and spec A, then, so I have a morphism from this guy to F evaluated to spec B. And here I have two morphisms to F evaluated at spec B, let's say that's B over A. That's the fiber product. And the requirement is that this is a equalizer diagram. Which means that this map induces a bijection between this set and the subset here, which consists of all elements where these two guys are equal.
Shouldn't this map be FPQC proper?
But yeah. For every, thank you very much. For every, that's very important. For every faithfully flat, let me write, flat and surjective. Surjective. Of course, right. Thank you very much. So, for every faithfully flat morphism of affine schemes, this sheaf condition must be satisfied. So we said, so clearly, if F is a sheaf, then indeed this guy is a co-equalizer of these two errors. I might confuse, there is a notion of equalizer and co-equalizer, so I'm confusing this two. So anyway, so it's clear that, so this consists of all elements here such that the images under the two arrows here are the same. And that's precisely should be F of spec A. So, okay, so that's the statement. And the proof, well, it's formal and it's boring. It will be omitted. I will not give it. Omitted. There is nothing really deep here. Okay. Now, back to the original question. Let's say theorem. So we discuss the following problem. So suppose you have map from scheme X and a surjective map from Y to X. And we have some scheme Z and an arrow here. And we assume that this map is constant on fibers. So this was phi. And this is P1, this is P2. And P1 composed with phi is equal to phi composed with P2. Okay. So assume that this map pi, assume that pi is a FPQC cover. Then there exists a unique psi such that the composition of pi and psi is equal to phi. Okay? So this is one application of faithfully flat descent. So here is another application, though, and well, I'm going to prove this theorem. That's not a formality, but I will derive it from a more general statement. Well, we descend a morphism here under a faithfully flat map. That's what it's called, descent.
Faithfully flat descent is this statement.
Well, again, it's a series of statements. This is one in this series. So I will give you another example, even more important example. Another question one could address is that, so given, say, a scheme over y, can you construct a scheme over x whose pullback to y is the original one? That's another question faithfully flat descent addresses. It's more delicate though. So we'll also discuss this. Okay, so what we are going to do, so I will prove this, but I will derive it from a statement about faithfully flat descent of coherent sheaves. So informally, well, I will formulate it in more general setting. We are going to have a quasi-coherent sheaf on y, and we want to descend it to x, meaning that we want to produce a sheaf on x whose pullback to y is our original sheaf. So, well, for this to be possible, this sheaf on y must be constant on fibers. And, well, not constant, trivial on fibers. So, so that meaning that the pullback of my sheaf on y to y times y over x, by the way, must be the same. We should be given an isomorphism. And then we are going to check that, well, so this is a necessary condition, and we will see in a second that it's almost sufficient. So I will formulate precise statement. Let's introduce some terminology. So let U be any sieve on X. So U locally given quasi-coherent sheaf on X consists of the following data. So, yesterday we discussed what it means for a section of a pre-sheaf, what it means to say that we are given U locally given a section of a presheaf. So here we kind of go by one step up in a categorical level. So we'll talk about not like sets, but rather objects of category. So, well, it's the following. So for every object, say U in X, this is an object of U, right? We're given a quasi-coherent sheaf. Coherent sheaf F of U. Secondly, for every morphism, say from V to U over X, we are supposed to be given an isomorphism between. So let's introduce some notation. So for every morphism phi, we are supposed to give an isomorphism rho of phi between f sub v and the pullback phi upper star of f sub u. So these are the data, and this data must satisfy a certain transitivity or closed-cycle condition. Okay, so I need more room. So the condition is the following. Such that, so for another morphism, for W to be let's call it psi over X, the following diagram is commutative. So I can take FW, and I can produce two maps to psi upper star phi. So I can compose this, right, this map to U. This is my phi. And so I can take my sheaf FU, and I can pull it back to this guy. So by B, we have an isomorphism between the pullback and this guy. So it's given by rho phi composed with psi. So this is an isomorphism. On the other hand, there is another way to construct an isomorphism between these two sheaves, quasi-coherent sheaves. So I can first use, this is my F, okay. This is FV. I can take, first identify these two guys using rho psi. And then I can identify these two guys using rho, well, using just pulling back this isomorphism here. So I take phi upper star of rho phi. Okay? And the requirement is that this diagram is commutative. Okay? So, well, so we define some objects, U locally given quasi-coherent shifts. These objects form naturally a category that I will denote by so this will be quasi-coherent U. Okay, that's the category of all U locally given quasi-coherent shifts. And so we have a functor from usual quasi-coherent shifts on X to this category that takes a sheaf F and assigns to it the following so I need to say the following collection. So for every U mapping to X, it assigns F U, which is phi upper star of F, right? So this object even need not be here, but for my applications, it will be in U. So, so I will leave you to produce this canonical isomorphism. It just comes from the transitivity of the pullbacks. So now theorem, which will be our main theorem about faithfully flat descent, is that if U is FPQC coverensive, then this functor that we produced is an equivalence of categories. Well, here is a baby example, first example of this. So imagine that you have scheme X, and U is generated by Zariski open covering. Say U is generated by two open subsets. So X is union of U1 and U2. Then unraveling the definitions here, so this is a category of quasi-coherent shifts on X, and this category is simply a category whose objects are triples, a quasi-coherent sheaf on U1, a quasi-coherent sheaf on U2, together. So I will write it. So quasi-coherent sheaf on this. Again, this is a covering. This is a sieve generated by this open covering, and it consists of triples F U1, Ui, and isomorphism between F U1 restricted to U1, U2, and F U2 restricted to U1, U2. Okay? So there, so in this case, it's Zariski descent, which is, I think, well known. Okay. So we will have.
You mean Q of U is this
Yes, yes, it's triples. FU1, FU2 plus an isomorphism. Yeah, by the way, one remark about the previous theorem that I should have made. So we discussed descent, faithfully flat descent of morphisms, right? So sorry, I should have said it before. So remember, okay, maybe since I forget about this, I'll say it later once we discuss a proof. So, okay. So this is the theorem is a weight generalization of this Zariski descent. So let me give you a non-trivial example. So, non-trivial example. Let's take, suppose I have a wet spec B to spec A, this will be my X, be a finite Galois cover in the sense we discussed earlier. So this is cover, and let's say this is U. Okay. And say its Galois group G is Galois code G of X, right? So let's try to understand what it means explicitly. What is this category? So U is generated by this single Atal cover, so it's a FPQS cover by U to X. So, okay. So let's try to. I'm going to use kind of. So let's see. So we have X. So what is this category? So first of all, we are supposed to be given a sheaf on quasi-coherent sheaf on U. Quasi-coherent sheaf on U is the same as module over functions on U. It's the same as a B module. Secondly, we are supposed to be given, well, I need to give myself something for any object of this sieve. So one object is, I can take U times U over X. So I'm supposed to be given something here, right? So this is, so here I have FU, and here I have, this is P1, P2, and I'm supposed to be given FU times U over X, and isomorphism between these guys and P1 upper star of FU, and P2 upper star of FU. So in particular, so I have a sheaf here, quasi-coherent sheaf, and I have an isomorphism between between its two pullbacks to this fiber product. So, okay. So, well, there is one extra. So we're given, again, we have fu, and we have this isomorphism. Let me give a name to this. I will call it rho. So f p1 upper star u and p2 upper star fu. So, and this isomorphism, so again, I'm trying to describe this category for you. So if I have an object of this category, in particular, it gives me this quasi-coherent sheaf f sub u together with this man, together with this isomorphism. But it gives me, this isomorphism satisfies certain property. Let me first formally kind of explain informally this property geometrically. So here is my u, and here is my x. So I have, well, maybe a point here, x, and I have the fiber over this point. So this is x, and I have fiber. So this isomorphism in particular tells me that the fiber of f, I'm given a sheaf on u. So, and this isomorphism in particular tells me that the fiber of this over u1 is isomorphic. We are given an isomorphism between the fiber at this point and at this point, because they are the same, they project to the same point in x. Right? So now suppose we have another point in the same fiber, u3. So then we can look, so this is u1, this is f u2, and then I have f u3. So then, well, in fact, I can construct two different isomorphisms between this guy and this guy. I can either identify directly this using only u1 and u3, these two fibers, or I can first identify it with this fiber and then compose it with identification between these two fibers. And I want these two isomorphisms be equal. That's my condition. So let me formulate it now precisely. So I have u times u over x.
So in our first example, the recycling condition was met.
Yes, exactly. So, and what is this? So I will take, I will consider two sheaves on this scheme. One sheaf will be P1 upper star of Fu. So P1 here stands for the projection. Well, P1 stands for many things. So here it stands for the projection from this guy to U, just projection to the first coordinate. And here I have P3 Fu. And now I claim that these two sheaves are isomorphic in two ways. So how they are isomorphic? I can take P1, 3 upper star of rho. So I first project, forget about the second coordinate. So I project here, and then take the pullback of this rho. Or I can take the composition. I can first identify, let me Okay. Should have said here P2 upper star of F U, and then this. So I will not even maybe, okay, so what are these maps? So this is P1, 2 upper star of rho. And this is P2, 3 upper star of rho. So I want this diagram to be commutative. Well, sorry, these two maps, yeah, be equal. So this composition must be equal to this. The two ways I identify the pullbacks of this sheaf on U, this triple product must be the same. So I claim, and this is an easy claim, that's a formality, that an explicit, by definition, P3 это просто проекция отсюда сюда. Проекция на третью координату.
Тут не очень хорошо, у нас P1, тут у нас 2 P1.
Хорошо. Но вот это изоморфизм между двумя пучками здесь. Значит, какими пучками? Я беру проекцию на первую координату отсюда сюда и обозначаю обратный образ относительно этой проекции вот так. С другой стороны, я могу взять проекцию на третью координату, и вот я обозначаю вот так. Теперь я утверждаю, что эти два пучка, что если у меня есть объект отсюда, то он приходит вместе с двумя изоморфизмами. Точнее, просто, если у меня есть просто вот такой изоморфизм ρ, то с помощью этого ρ, одного ρ, я могу построить два изоморфизма между этим пучком и этим пучком. Вот я их тут написал. Но утверждается, что если мой f приходит отсюда, то вот эти два изоморфизма равны. Вот я сейчас это напишу. So quasi-coherent sheaves on U is just the category of triples. Well, pairs rather. So it's FU, FU isomorphism ρ between these two guys. This happens, this is isomorphism of quasi-coherent sheaves on U times U, and this is ρ. And this isomorphism is subject to the following condition. This is a condition that pi1, 3 upper star ρ is equal to 1, 2 upper star ρ composed with pi 2, 3 upper star ρ. Right? So I consider the category of pairs with this property. So a very good exercise, which is again a formality, to check that this is indeed an equivalence. I will not write down details. It will be boring, though important. So let me sort of. Что? Да, совершенно не важно. Здесь могло бы быть вообще здесь отображение из U в X могло быть любым отображением, любым абсолютно. Даже не обязательно суръективным, не обязательно плоским. Я рассматриваю решето, порожденное U. И тогда категория, вот эта категория квазикогерентных пучков на этом решете, локально заданных, это вот это. Теперь, значит, почему... Давайте я попробую объяснить, почему, как построить вот. So I will explain how, given this datum, you can construct an object here. So construction is simple. So suppose what we are supposed to do, we have u, we have x, and we have any object of our sieve generated by this guy. So what is an object of this sieve? This is a scheme W over X, such that this structure morphism factors through U, not uniquely, right? So our condition is that there exists at least one map that makes this diagram commutative. That's the condition. That's so this W to X is in this sieve generated by U if and only if such arrow exists. Okay, so then so once I choose this, map, let's give it a name, say phi1. I can define fw to be phi1 upper star of fu. That's very good, but that's not. It's not yet well defined because there could be two maps that make this diagram commutative. So I need a way to identify the two pullbacks. So in order for this to be kind of well defined, I need to explain how these two guys are identified. Okay. So the answer comes as follows. So if you have two maps that make this diagram commutative, you can produce a map to U times U over X. And it's given by pair, phi1, phi2. And once I have this, so there are two projections here. So I can, so these two arrows, well, their composition of this arrow and the two projections, so I can define this map to be phi1, phi1, phi2 upper star of rho. Okay. So very good. So we are now almost. So our goal is to define an object of this category, right? And for any W, we produce something. And well, so this something kind of depends on the choice of this map phi I, but we produced an isomorphism between the two pullbacks. But now suppose you are given a third map. To make it really well defined, you have to do the following. So if you are given a third map, then we can also consider this. And so, well, just by changing notations, we now have an isomorphism between this and this, right? But we could also construct an isomorphism between this and this by composing this isomorphism and this one. And really, to make it really, this f sub w really well defined, you need to check that this isomorphism is equal to the composition. And that's what this whole cycle condition that I wrote here is needed for. Okay? So once you have three maps, you can produce a map from W to U times U times U, and then the commutativity of this diagram amounts to this property, or follows from this property. Okay? So this is an explanation why this is an isomorphism, why it's an equivalence of categories. Okay, so as Dima observed, so far we didn't use anything about the map from U to X. Now, so let's go back to our setting when so we have, so what is our U? So U, okay. So U, so we have U which is spec B, and this maps to X, which is spec A, and here we have U times U. Okay. So, and they have two projections. So U times U over X. So imagine that we have a, so now assume that this is a Galois cover. What is U times U over X in terms of the Galois group? I claim that this can be identified with U times G, just over spec Z. Right? So why that? Well, so if you have a point U comma G, what you do, you send it to U comma G of U. Remember that G acts on U. So this gives me this map. These are maps between finite Galois covers of X. And it's an isomorphism on a fiber, one fiber. Just take any fiber over a geometric point. So it must be, because the fiber functor is conservative, it must be an isomorphism. Right? So now what are these two maps here? So these two maps. So one map, okay, maybe too many errors, sorry. Not. So this map, one map is simply projection. Projection, well, P1. Another map is the action map. So it takes pair U comma G to G applied to U. So G acts on U, so you have this map. So in other words, what we have is so unraveling, now going back to this description, so we see that, let's give a name to this. Let's call this map action map, so action map phi. So we have, so what is this? So we have a sheaf F U, and we are supposed to be given pi 1 upper star, an isomorphism between this and the pullback with respect to the action map. Well, so this, so if I erase this condition here, then a pair like this is simply a quasi-coherent sheaf on U together with an isomorphism. This is my rho. But now, so let's try to formulate explicitly what this condition means. Это накрытие ГЛО, в частности, свободно. Okay? So, да. Okay. So, so what does it mean to have this? What it means explicitly in terms of this action, this second condition, the transitivity condition. Wait. So let's think for a second. So we are saying here that the fiber of our sheaf at a point u, small u, is isomorphic. Well, we are given an isomorphism between its fiber at point g of u. So a much better notion is a notion of equivariant sheaf, right? So suppose you have now 3 points, g1, g2, then you have identification. There are 2 ways to construct an identification between the fiber at point u and the fiber at point g1 times g2 times u. So, well, if you this is g, this is u times g times g. So this condition, third condition, is expressed by as follows. So you it's equality of 2 pullbacks here. So I will formulate now the answer. Well, first of all, I claim that this category is equivalent as the category of G equivariant quasi-coherent sheaves on U, and I will tell you explicitly what this means. So instead of writing another time a diagram like an identity like that, so I will tell you in terms of A and B. So B modules with an action of G such that B modules M with an action of G such that G of B times V is equal to G of B. So G acts on B times G of V, right? So it's simply a category of B modules with a semi-linear action of G. Semi-linear means that it's not linear over B. It rather satisfies this condition. Okay? And so let's see what, with this description in mind, so let's see what this theorem assumes. So, so we get a quasi-coherent sheaves on X, which is just A modules and we have this quasi-coherent shapes on U. So what is the functor that we discussed? So it takes n here to n tensor it with B. And so what is the action of G here? Well, G acts here while its action on B, right? Because it acts here. So this gives me the functor. And the claim, the theorem, asserts that this is an equivalence of categories. Therefore, well, any B module with a semilinear action of G is of this type. So let me finish just by, let's think what could be the inverse functor. Invariant. So M goes to M times G, just G invariance, right? So this is really surprising because usually G invariance is not an exact functor. So, well, if you have an equivalence of categories in particular, the functor is this inverse functor must be exact. So in particular, well, for similar interaction, the claim is that it's exact. So here is a baby example of this. Suppose you want to describe the category of real vector spaces. So the assertion is that it's the same. So take for X just spec R, and for U spec C. Then the claim is the following, that the category of real vector spaces is equivalent to the category of complex vector spaces together with a semilinear action of the group Z mod to Z, which is semilinear in the sense of complex conjugation. So the functor is the tensor product functor. The opposite functor is invariance with respect to Z mod to Z action. So, OK, so my time is over. So that's all I say today.
I have a couple of questions.
Yes.
On that. So the field extension is always faithfully flat. So we should be able to decide with respect to every field extension.
Inseparable. You want to take inseparable.
No, first, one thing I really want to take is C over Q. I want to set something from C over Q. So do I do just the same and take all automorphisms of C over Q?
So is it true that, so you're saying that C over Q, C times C over Q, is it the same as C, what was, how I should say it, it's probably just, so product, is it the same, is it true that this algebra is isomorphic to product? Product makes sense, right? Product over OG in automorphisms of C over Q of copies of C.
No, because you guys have different cardinality probably.
So this, I don't know. Well, what is a...
On the left-hand side, we probably have continuum, and on the right-hand side, we probably have more.
Well, so again, so for finite field extension, the argument was, for finite Galois extension, the argument was that, so you get a map, and then you compare dimensions. So here,
Isomorphisms are more than continuum, right?
probably, so I doubt that this is true, but.
Something, right? Faithfully flat descent.
Yeah, yes. So you can formulate it in terms of this, but I don't know how to compute this.
So even
Ну, на что угодно. Нет, ну тут
Okay,
ну,
we know how to descend from Q bar to Q. This we know. So we may reduce this to the question to how to descend from C to Q bar. Is there an answer to that question?
well, definitely. So sorry, maybe. So definitely, these two guys are not isomorphic. There is even no map from this infinite direct product to this guy because it's not the same as given the collection of maps from each factor, right? So forget about this. So yeah, I don't.
Let me see what I want to do.
Yes.
Consider a factor of all families of elliptic curves with a marked point of order 11.
Yes.
We can prove that over C is represented.
Yes.
So I want to reduce the C to something small. What can I do? Can I do something from this theory?
Yes, you can. But not from this was kind of example that I mentioned, but not really explained. So another question. Okay. Suppose you. Very good question. So suppose you are in the following situation. You have a functor from schemes over Q to sets. And you know that if you restrict this functor to schemes over C, it's going to be representable by an affine scheme. So suppose you, for some reason, you know that your moduli space is affine of marked elliptic curves. Then you know that then the theorem implies that it's representable over Q. So in your particular case, example, it works. So the modular curve is affine. Provided that you don't care, well, if you don't, like, if you consider like the honest modular curve, not a compactified version of it.
So the case with flat sets theorem should apply.
Yes. So how you work, how you prove this? So you have an algebra over C that represents your modular curve, and all you need to do is to produce an isomorphism of the two tensor products of this algebra with this. And I claim that this isomorphism is given to you because you have a functor defined over Q.
So you consider your module product over this sphere.
Yes, yeah. So for non-affine schemes, it's more complicated. So it's okay for projective schemes, but for quasi-projective. But in general, it doesn't work.
Because it descends the idea.
Yeah, yes. Okay, so let's stop here.